So let's go ahead and talk about maps before we talk about ethics papers. Maps. Oh yeah, treasure maps. See, you didn't even have to word maps on the screen. Therefore, it has to be. Well, good. I was just turning off the light. Okay. So beforehand, we talked about sets. What was so nice about sets?
They're easy to keep track of. They're easy to sort. Not sort, but keep in line.
What's the fast operation on sort? Maybe we'll ask it that way. I think you might be on the right track, Tyler, but I can't tell.
When you have to find something.
When you have to find something, right. So sets are great for finding something. And what's better when, or why would you use a list instead of a set?
You need to add something.
Index.
Okay, sure, indexing, but what do you use a list? So why would you use a list over a set? Or a set over a list?
It's a list. It's a setup.
What was slow on a set? Remember?
A set was the unindex thing.
To go through it, iterate through it. Right, so you want to use a list. There you go. You want to use a list if you're going to iterate through all the objects often. And use a set if you want to just ask, do you contain this? So a map is going to be kind of like a set, but instead of do you contain this, it's what is the value of this key? In other words, you're mapping a key to some value. A very common example to this is if you have a student and you know maybe you know their ID number, you want to be able to map the ID number to the student, so you use a HashMap to where when you pass it the ID number, it would give you all the student's information. So the point here is key value pairs. Beforehand in a set, we were just asking, do you hold something? In a list, you just go through items. So everything's are singletons. You just have one item for everything inside of it. With a map, you have two items per an entry, I'll say. And it's the key and the value. So you say, here's the key, what's the value? So there's the map interface, and then you have the hash map, hash table, and tree map. Just like beforehand, the hash map uses a hashing, which we talked about a little bit. And then the tree map uses a tree, namely a red, black, or a type of binary tree. And don't worry about linked hash map. So it does preserve at least the insertion.
Just one more time, just really, really quick. Can you just reiterate what binary tree is?
Sure. Binary tree. Whoa, I'd never played the camera. Let's load that up. Whoop. All right, so a binary tree is a tree where every node has up to 2 children. So.
The triangle is the glare. Yep.
Good, thank you.
That is actually that's pretty good.
That is actually pretty good. All right. So, you always have a root node. Maybe we'll give it 99. And it might have two children, 80 and 120. So that's a binary tree, because every node has at most 2 children. So I could do 75, and then over here I could do 140. That's a 1, by the way. That's still a binary tree, because every node has at most 2 children. Naturally, I could add another node right here, and maybe another one, 101. Okay, so still a binary tree. What would violate the property is if I gave this guy another node, like 100. Then he's no longer binary, he's, I guess, trinary. That's the best way to put it. Well, yeah, so that's a binary tree. You start at the root, and then you can go down.
And what's it for?
Storing data. So like a linked list holds data and, as a long list. A binary tree also holds data, but you have a root node, and then you need to go down the tree. The point of this is that, think of your binary search. If you're in this and you're trying to find 101, and I've already given this binary tree, what's called a binary search tree, a strict ordering, you look at the root node 99 and you ask, are you greater than or less than? And then by being greater than, you know to go to the right of the tree. Then you go to 120, and then you ask, are you greater than or less than 101? Well, 120 is greater than, so you go to the left. Make some sense? All right. Did I answer your question? Awesome. Okay. So the map interface, key value, associative array is also what it's called. Hash table, associative array, hash map. You can just think of them for all intents and purposes as the same thing. So look up you look up via an index. So you're going to put the key with a value, and then later you can get the value by asking the key. And of course, you can also ask if it contains a key or contains a value. All right, let's go do some examples, because that's probably the part where this all makes sense. Hash map examples.
But I can say honestly, this is last semester I was gone for this, so like.
I understand.
This one I was lost.
Okay, so first off, we create a map. And what do we want to map? Something to something. Map an integer to a
String.
string?
Yeah.
Okay, we'll do it to a string. All right. What should we call this? What are the integers and what are the strings?
We're gonna link cars to the horsepower.
Okay, so horsepower to cars, right? Yeah. So. Okay. I'll just call it cars. It was new hash map. Boom. All right.
And I've always wanted to ask this. Why is it that you have to put the greater than less than symbols and then the parentheses as well?
Well, you need to do the parentheses to tell it that you're calling the default constructor. The less than and greater than are basically telling you that we're using generic, which were defined previously on the map. Welcome. Okay, so if we want to put something in here, we could do cars dot put. All right, go ahead. Horsepower?
647.
647.
All right.
What is it?
Ford GT.
What year?
2017.
2017 Ford GT. All right. Wow. Go ahead, Tyler. I let Nicole go first.
707.
707. What year?
2015.
2015. How do you spell it? Just H like this?
Yep.
All right.
Dodge. Okay.
Ah, Dodge. That's good.
It's actually the Charger or Challenger, and that's their upgraded package.
Oh, okay.
Like, it's pretty fast.
Anything else?
Yeah. It's 2012 Mustang, and the number's like 253.
What is it? 2012.
2012 Mustang.
Okay.
Ford Mustang.
I'm trying to remember what mine is. I think it's 140.
What is it?
65 Dodge Dart.
Wait, that's all for the car?
65. Yeah, well, it's
Stock motor?
yeah. Oh yeah.
Oh.
Oh, stock. The other thing about it is the horsepower and torque are the same.
No.
Yeah. So it's a little-
235 horsepower.
35? I was a little off. And the torque is probably pretty close as well.
Doesn't talk about that.
Doesn't talk about. Torque is your friend. Anyone else?
Oh yeah, we can do the Pontiac Trans-Am. 375.
375. What year?
Girl, my transmission's like full of trailer. Oh yeah.
Pontiac Trans. Is it one word, Trans Am, or two? All right.
It's weird because it's just the name of a race and the name of the car.
Yes. All right, so the point of this is you can do system.out.println, and maybe we can do cars.get, and we want what has 647 horsepower, and then when we run it,
Oh wow.
So yeah, dot get, there we go, 647. Cool. All right. So that's a simple example. Let me go ahead and push it up here. Public static void simple example. All right. What's important to understand is, since the map, simple example. All right. So the map can be pretty much of anything, and I think we already have a student, don't we? Yeah. Let's see, what does a student have? Oh, it has ID number and name. Beautiful. So if we wanted to, we could also do integer to student. We'll go ahead and call this students. And in here we could do students dot put. Maybe we have an ID of 1, 2, 3, 4. Maybe I should spell students correctly. There we go. New
What
student.
application would this have in a normal situation? Like, what would be the time you want this?
Doctor.
Or maybe a time you use it.
So these are used all the time. And hold on, let me figure out what I did wrong. Oh, because it's actually backwards. And then I can literally do system.out.println. I'll answer your question in a bit. Students.get 1, 2, 3, 4. Forgot the S. Does it already have a toString function? Let's find out. Nope, doesn't. So I can do dot get name. Okay. All right. So it's using a hash table in the back end. So how fast is dot get?
Fast.
Really, really fast. So whenever you want to do a basic search on, I will say, non-incredibly large data sets, normal data sets, you really want to store everything in a hash table. I mean, you can put your cars all the way in there by horsepower, so you can store them by horsepower. Create another hash table to store all the students by ID number. Really, whenever you want to store something by something simple, that's what a hash map is really good for. And that's used a lot through all your applications. Fortunately, it's fortunately it's real simple, but that's about all there is to it. Hash maps are used extensively. Any other examples you want me to go through here? Okay. Okay, hash map based on hash map, constant time for insertion and locating pairs, most commonly used. And when I say most commonly used, I mean these hash maps are used all over the place. Sometimes people will use them instead of lists because they're just so quick on just finding something. Linked hash maps, it basically preserves order if you need to ever iterate through it, but try to avoid it. It has some extra overhead. And tree map, what's nice about it is it actually gives you everything in sorted order. All right. I do want to talk about performance real quick. We're not going to go through binary. We will go more in depth with binary trees and data structures, which is what a tree map is built on. Same thing with a tree set. But I want to touch base on at least some performance. So adding is O of 1. If you recall, with adding, you just have to make the hash, jump to the entry in your array, and then add it to the linked list, which is all. Those are all O of 1 operations. So adding to a hash map is actually really fast. The tree map is a little slower, but actually still really fast because it just has to iterate down the tree, which is log of n times in order to find it. Clearing, I say O of 1-ish because you have to basically delete the array. Get is pretty fast on hash map. Tree map still log of n. Remove, but really get, remove, and set is all going to be O of 1 on a hash map because you just jump to the correct location in the array because you're using hashing, and then you perform that operation on a linked list, which in general is very small. Union/intersect, that's talking back to hash sets. O of n is that it's actually pretty fast, where n is the size of the two arrays, or your two sets, I'm sorry. And that has to happen because you have to go through it. The big advantage here is if you ever need to sort. On a hash map, you would have to do a full sorting algorithm, while on a tree sort, you don't have to because it maintains sorted order the whole time. So the advantage of a tree map is if at any time you need to run through it in sorted order, you just can go right in and do it. There's no extra building cost to it. Okay, basically you need to use maps. Go ahead and use a hash map unless there's a good reason to use a tree map or something else. That's all there is to it. All right, any questions about maps? I know it's early in the day, but we need to just finish this up real quick. Nope, okay. All right, quick summary. There are actually a lot of solid principles being used here. Single responsibility, yes. What are they?
Yeah, it's the single responsibility, the dependency inversion principle.
Yeah, those are the two big ones. So with single responsibility, do notice that all these classes, collection, list, set, map, all of them all have one very simple role or responsibility, and they don't deviate from it. They don't try and add anything to it. The reason that's good is because it's helping you give you a clear picture of what the object is supposed to do. LSP, no one is violating this. You're not having a list isn't trying to do something. The duck principle. You know, the list interface isn't trying to do what a map does. It's only sticking to what a list does. So it's, again, helping you be clear on what each object does. Integration, segregation principle. Basically, the interfaces are straightforward. There's no, I guess, wackiness or strange. You know, which function do I need to call at what time? You know, you can add to it. You can remove from it. There's no, I guess, weird adding or weird removing. There is some add to front, add to back, which is helpful, but it's not like there's some multiple ways to add to the front. There's just one way to add to the front. And dependency inversion, this is the most important one. Notice that list, set, and map are interfaces. They're not actual objects. So what happens is that while you think about it as a list, if at any point you need to jump from an array list to a linked list, you just need to change at the very top of your code, you know, new linked list or new array list. And lastly, we talked about hashing, which is a very important technique and widely used for performance. We'll go in more depth about that in data structures, but at least understand how it's being used for this class. Okay. Anything else on this before we go into your ethics paper? Nope. All right.